A rectangular wireframe shown in figure has a width d, mass m, resistance r, and is of very large length. A uniform magnetic field B exists to the left of the frame as shown. A constant force F is pushing the frame into the magnetic field at t equal to 0. We have to calculate the acceleration. Now one thing you have to understand here is that due to this force the frame will move to the right hand side, and due to which it will start entering into a magnetic field. Now due to which the change in magnetic field is observed, so the EMF will be induced, current will flow. If current is flowing, then the force will act on the rod, and if the force is acting, then the F net will be given by this force minus the force due to magnetic field. Fine. Now clearly that magnetic field is inside, so the current that will be generated will be in downward direction, so the force that will be acting on this rod will be right hand side. This is F magnetic. Now we have to calculate the velocity, or we have to calculate the acceleration when the velocity is v. Now let's suppose at this very instant the velocity is v in this direction, so the current in the rod, or the EMF, I should write the EMF that will be induced at this very instant will be given by B into V into D, because the length of this rod is D, and the current will be given by BVD by resistance. Now this is the current through the rod, so the force magnetic will be given by magnetic field into the current, that is BVD by R into length again, so it will be D. On solving this I get B square V D square by R as my F magnetic. Substituting this value in above equation, I have F net that can be written as mass into acceleration as F minus B square D square V by R. So the acceleration that is coming out, that will be equal to RF minus B square D square V by MR. This is my answer for the first part. In the second part, I have to show that after some time the frame will move with a constant velocity till the home frame enters into the magnetic field. So clearly, if the frame is moving with a constant velocity, so I can say that acceleration equal to 0. Now substituting acceleration equal to 0 in this equation, I have RF equal to B square D square V naught. Obviously, let's say this velocity is V naught, the constant velocity at which acceleration is 0. So V naught comes out to be RF divided by B square D square. That is my answer for the second part. In the third case, I have to show that the velocity at the time t is given by this. So let's say acceleration is given to me as this. Now acceleration can be written as dv by dt. So on rearranging this equation, I have dv divided by rf minus b square d square v is equals to dt by mr. I did nothing, I just brought this term over here and dt over here. So on integrating both sides, time varies from 0 to t, and of course initially the velocity is 0, so integration will be 0 to v. So substituting the value or solving this integration, we get integration as natural log of rf minus b square d square v whole divided by minus of b square d square is equals to t by mv. The integral limit varies from 0 to v. This is my capital R, this is also my capital R. Fine. So substituting the limit, we have natural log of rf minus b square d square v divided by rf is equals to minus b square d square t by mr. Now we know that this equation on rearranging I get b square d square by r can be written as f by v naught. So using this equation I'll substitute this over here. So I have natural log of 1 minus b square d square v by rf is equals to minus of f by mv naught into t. So on solving this I get 1 minus b square d square by rf into v is equals to e to the power minus ft by mv naught. This term is nothing but v naught, so I get 1 minus v by v naught as e to the power minus ft by mv naught. Solving this I get velocity as v naught into 1 minus e to the power minus ft by mv naught. That is my answer.